Welcome back. Let's continue our discussion of electrophilic aromatic substitution reactions by talking about sulfonations. Now, a sulfonation reaction is one in which the benzene ring reacts with sulfur trioxide to give you a sulfonic acid. This molecule is a relatively strong acid by all intents and purposes. It's a derivative of sulfuric acid ultimately. So it does have a pretty acidic proton. The pK basically it's in the -6 range, so it's to be considered a strong acid altogether. Now, the interesting thing about this reaction is that unlike the previous ones that we mentioned, the bromination, the chlorination, the alkylation, the acylation, this is actually one reaction where there is an equilibrium. So you could revert the reaction back to the unsubstituted benzene state. And the reason this happens is because sulfur trioxide is a very, very strong electrophile. Strong enough that not only does it react with benzene, but if you introduce water into your reaction, it will absolutely react with water to form sulfuric acid. And this, in essence, removes and diminishes the quantity, the concentration of sulfur trioxide present in solution, which by equilibrium will push the product back to the reactant side. So, as we'll see momentarily, we can always introduce sulfur trioxide or sulfonic acid group onto the benzene ring, only to later remove it after we have modified our benzene ring, accordingly. So this will be a very useful method to kind of block certain sites in the benzene ring and make them available later on. So typically speaking, you could even do this with just dilute sulfuric acid. That will do the trick as well. That's typically how this is done. But the idea is that, you have plenty of water to suck away the sulfur trioxide. Okay, so before I show you the mechanism of the sulfonation reaction, it is worth mentioning a couple things about sulfur trioxide. This often gets overlooked in many textbooks, and having an inorganic chemistry background, I feel like I should probably tell you a little bit about it. If for anything, just so that you're aware of how this kind of works out. All right, so sulfur trioxide is pretty strong Lewis acid, as I mentioned earlier, and if you bring that in the presence of plenty of sulfuric acid, so like concentrated sulfuric acid, you will form this derivative right here, this dimeric derivative, and together this mixture is known as oleum. And one characteristic of oleum is that not only do you form this pyrosulfate component, but you have basically fuming sulfuric acid. So anytime that you may have heard or seen, or in the future, whenever someone mentions fuming sulfuric acid, they're basically talking about oleum, which is a mixture of sulfur trioxide dissolved in concentrated sulfuric acid. And a good chunk of the mixture is the pyrosulfate. Now, the interesting and cool thing about this is that the phases do change as a result of the changes in molecular weights. So you have the sulfuric acid in your liquid solution. The sulfur trioxide is the vapor that you're seeing, emanating from the mixture. And if you store this reaction in a sealed vessel or a closed container, you'll even get crystalline products, which is basically the pyrosulfate being formed as a result of the sulfur trioxide not being able to escape from the flask. So you actually get to see all of this dynamic equilibrium happening on these reactions. It's rather a cool thing to see. So this flask, obviously, you have the liquid, which is your sulfuric acid with some sulfur trioxide dissolving it, and then you have the pyrosulfate solid that has been formed right here. The pyrosulfate, just for your information, at 36 degrees you get to melt it. So it's not a very robust solid in terms of the amount of heat it can take before it melts. But in your typical chemistry laboratory, where the temperatures are usually kind of chill, kind of cold, on purpose, right, to prevent the volatilization of many compounds, this will probably be a solid. All right, so what you basically end up doing is you react benzene with oleum. So it's not pure sulfur trioxide because that's just a gas, but it's the oleum mixture that you bring them in contact with. And this being a really strong Lewis acid, the benzene ring has no problem donating its pi electrons to create a new bond onto sulfur. And also, what you have to do is kick away one of the electron pairs of the sulfur oxygen bond. So you end up forming this intermediate, this sulfonate intermediate, which also has created, you might say, Heimer complex, right? Because the two electrons of the pi bond have been used to create the carbon sulfur bond, but it has come at the expense of leaving one of the carbons with only 6 electrons. So you still form the Heimer complex. Now, you have sulfuric acid and you have, of course, hydrogen sulfate as an equilibrium mixture. Now, granted, probably you're not going to have a whole lot of hydrogen sulfate since this is concentrated sulfuric acid, but you'll have enough of it that it can act as the base to remove the proton of the Heimer complex and reestablish the aromaticity of the ring. So at this point, you have your sulfonate derivative, you have your conjugate acids, your sulfuric acid as a byproduct, and you could use that very same sulfuric acid to protonate your sulfonate. Okay, so you basically go back and forth with the protonations. Basically, all this is nothing more than proton shuffling from a carbon center ultimately to an oxygen. And yeah, you could basically look at it that way. So as far as the important information, of course, is the mechanism of this reaction. Now, whether you remember that oleum is a mixture of sulfuric acid with sulfur trioxide turning into pyrosulfate, that would be a bonus, but the important thing is the mechanism. So just keep that in mind. All right. Oh, and one more thing to keep in mind, as I mentioned earlier, you can use the sulfonic acid group as a blocking group for the benzene ring. The moment you have it installed there, there's not going to be any further substitutions done on that particular carbon. But later down the road, you can always remove this sulfonic acid group just by treating this molecule with dilute sulfuric acid. Okay, so let's talk about a somewhat similar reaction, the nitration reactions. In the nitration reaction, you do react your benzene ring, your aromatic ring, with the NO2 plus cation, which is a strong Lewis acid. And all you end up doing is installing a nitro group onto the benzene ring by doing this reaction. Now, the nitronium ion, the NO2 plus cation, is not something you can necessarily have as a reagent. You usually make this in situ. You'll prepare it right as you're about to do the reaction. And the best way to do this is to simply react your nitric acid, which is the source of the nitronium ion, with something stronger. You could use sulfuric acid. You could even use HCl, but sulfuric acid kind of does the trick, because if you look at the pKa's, sulfuric acid has a pK of -10, nitric acid has a pK of -1.7, and they're both strong acids. Don't get me wrong, they're both strong acids, but they're strong acids from the point of view of water. From the point of view of each other, if one is to be an acid and wants to be a base, sulfuric acid is the acid, the thing with the lowest pKa. And nitric acid will have no choice but to behave as the base in this reaction. And at first you might think that that's very, a very wrong thing to say, perhaps a little bit, a forbidden thing to say, but the reality is that the pKa's do what they do. Okay, now notice this as well. This has to be concentrated for this to work out, because the nitronium ion is very reactive. Reactive enough that it will react with water to give you back nitric acid. So you need to have high concentration. So notice here that this is 98% concentrated sulfuric acid. And for nitric acid, we have about 60 to 70% concentration. So these are really high concentrations. In terms of molarities, we're talking about anywhere from 12 to 18 molar concentrations. So highly concentrated, highly corrosive. So if you react these things at 0 degrees Celsius, And you do it this way. You do 1 part of sulfuric acid to 1 part of nitric acid. This is good enough to ultimately generate an intermediate that looks like this, where you end up with 2 protons on one of the oxygens, and as such, you create a good leaving group on what used to be nitric acid. So what will happen right here is that the lone pairs of the oxo group right here will move over to the nitrogen, and in the process, you'll kick out water, thus forming your nitronium ion. So once you form the nitronium ion, Benzene ring attacks the nitronium center with one of its pi electrons. You create the Meissenheimer complex like we talked about in the past, and the hydrogen sulfate that you have present in there as a result of having sulfuric acid in solution can come by, attack the proton, kick those electrons back to the carbocation to reestablish the aromaticity of the ring, and at this point you have generated your nitro group altogether. So the mechanisms are not fully different from each other. In fact, they all kind of share the same overall similar initial steps. But what we're going to see right now is that due to the nature of the substituent, we have different outcomes that can happen after the first substitution. But we're going to save that discussion for the next video. So I'll catch you there. Bye-bye.